Hello, I hope you're having a good day. My name is Escobedo and I thank you for attending to this presentation. This poster, titled Synthesis of Ulmium Diboride Based Bulk Magnetocaloric Alloys by Arc Melting, provides an overview of my master's work and addresses the synthesis and magnetostructural and magnetocaloric characterization of the alloys ulmium diboride and ulmium gadolinium boron with the composition you see on the screen. It is worth mentioning that to this date, ulmium diboride is the material with the best magnetocaloric properties for cryogenic applications, such as hydrogen liquefaction, and these alloys were obtained through electric arc melting. It is important to note the difficulty in synthesizing these alloys due to the differences in melting points and densities of the rare earth elements and boron, as well as the presence of the antiferromagnetic phase ulmium tetraboride. This is reflected in the fact that 8 meltings were necessary in both cases to achieve homogenization. The magnetocaloric properties here obtained are outstanding, as our results are comparable to those reported in the literature. Well, as you may have heard, one of the most promising proposals to replace fossil fuels is hydrogen, as it produces only water vapor when combusted, making it one of the best clean energy resources available. However, due to its low density in gaseous form, its use requires the necessary technology and infrastructure for liquefaction, as well as for storage and transport in liquid form. Hydrogen liquefaction can be achieved through magnetic refrigeration, which is based on the magnetocaloric effect. The magnetocaloric effect refers to the heating or cooling of a ferromagnetic material under adiabatic conditions when exposed to a change in an external magnetic field. This phenomenon is described by two physical quantities, the adiabatic temperature change and the magnetic entropy change, which are measured as a function of temperature for a given variation in the magnetic field. The objective of this work was to synthesize the alloys ulmium diboride and ulmium gadolinium boron using electric arc melting, and to characterize their magnetostructural and magnetocaloric properties. In this experimental section, we can observe the characterization techniques that were carried out: X-ray diffraction, scanning electron microscopy, and the magnetocaloric and magnetothermal characterizations. Also, we can see the equipment used for these measurements. From the magnetization measurements under an external magnetic field of 5 millitesla, the created temperature of both alloys was estimated, calculating the derivative with respect to the temperature. Regarding the magnetocaloric properties, the magnetic entropy change curves were obtained through the numerical integration of Maxwell's relation using a set of isothermal magnetization data. In figures 1a and b, we see micrographs corresponding to the ulmium diboride alloy. The first one shows the alloy microstructure, where the darker regions correspond to the ulmium tetraboride phase. The second image shows a higher magnification micrograph, where we can see preferential grain growth along the solidification direction. In figure C, we see the microstructure of the gadolinium doped alloy, which is more homogeneous. Now, through X-ray diffraction analysis, it was determined that the main phase in both alloys has a hexagonal crystal structure with a space group PC/MMM. Ulmium tetraboride was also detected as an impurity phase. Figure 2a shows the readable refinement for the ulmium diboride alloy, indicating that the aluminum diboride type crystal structure is the predominant phase with a volumetric presence of 98.95%, while the remainder corresponds to the uranium boron 4 type structure. In table 1, we summarize the information for these two phases, including the crystal structure, space group, and lattice parameters. In figures 2b and c, we show the magnetization curves measured at 5 Tesla and 5 millitesla. In both cases, for both alloys, we see that we have a high saturation magnetization, which could influence positively in the material's magnetocaloric response. Additionally, the absence of anomalies in the 5 millitesla curves indicate that we have no presence of other magnetic phases. The insets in both figures display the derivative of the magnetization as a function of temperature. The Curie temperature for the ulmium diboride was estimated to be 16 Kelvin, while for the gadolinium doped alloy it was estimated to be 25 Kelvin, temperatures that are close to the hydrogen liquefaction point. Well, in figures 3a and b, we show the magnetic entropy change curves for ulmium diboride and ulmium gadolinium boron respectively, for variation fields from 1 to 5 Tesla. We observe that the maximum values in both cases are quite high. For ulmium diboride boron, for ulmium diboride, we achieved a maximum magnetic entropy change close to 40 joules per kilogram Kelvin for a 5 Tesla field variation, which is extremely high. And we can also see peaks at 12 and 13 Kelvin in both figures, which are associated with the spin reorientation of the system. For the gadolinium doped alloy, in the curves for 1 and 2 Tesla, we can see a plateau shape between the 13 and 23 Kelvin. A highly desirable feature for these applications. As mentioned in the experimental section, these curves were obtained from a set of isotherms that we can see on the insets, and integrating them with the Maxwell relation. The refrigeration capacity of these alloys was also calculated under certain criteria reported in the literature that we can see in these equations. As seen, the values obtained are quite high, and we can see them in the figures 6. The inset graphs show how the temperatures of the hot and cold receivers vary with respect of the magnetic field variation. And well, these hot and cold receivers represent the working range of the temperature, the working range of the alloys. In table 2, we summarize the main magnetocaloric properties of the alloys and the comparison with some other alloys having a Curie temperature close to that of the hydrogen liquefaction. We can see that we obtained pretty good properties for the synthesized alloys in this work and are comparable to those reported in the literature. I remind you again that these alloys have the best properties for hydrogen liquefaction applications. And we conclude that the experimental challenge posed by preparing these alloys was successfully overcome. Both alloys crystallized into the hexagonal phase that we mentioned before, and we have a little ulmium tetraborate impurity. For both alloys, the values of the magnetic entropy change and refrigeration capacity are comparable to the best reported in the literature by other authors. And I want to thank CONACYT for financing this work, and the EPCYT for being my home in these master studies. Thank you.